To understand the motion in two dimensions, it's very important for the student to realize that any velocity or displacement or acceleration in two dimensions must be defined in a proper way. If you work in Cartesian coordinates, for instance, you should know that the displacement has two components, delta x and delta y, and the velocity as well has two components, v sub x and v sub y, and the acceleration as well. Now, the velocity vector equation v equal v naught as a vector plus a t can be rewritten as this, because this component that accompanied with I hat is v sub x, that's the x component, which is in one dimension is defined as v naught, or v naught represents the initial speed or initial velocity, plus ax t. That is the velocity along the x-axis with a constant acceleration. And the other component for the other motion is vy, the final velocity along the y-axis. The component of the y is v naught y plus ay t. So now, if you look at this equation, this is a velocity vector of vx, v sub x I hat plus v sub y j hat. So the first one along the x-axis represent a motion, and the second one represent a motion, and these two motions are independent of each other. Also, for delta r, for the displacement, we have the product of a velocity initial with time plus half the product of the acceleration as a vector multiplied by t square. This is also equivalent to this. As you write, delta r equals delta x I hat plus delta y j hat, where delta x in one dimension, displacement along the x-axis, has this relation when you have a uniform also motion with a constant acceleration along the x-axis. This is v naught, the initial velocity multiplied by time, plus half a sub x t square. And this is the correspond also for delta y along the y-axis, v naught y t plus half ay t square. So obviously from these two latter relations, you can also set that v naught as a vector equals v naught x I hat plus v naught y j hat. We can get it from this equation. If we got this v naught as accompanied with I hat, and got v naught y, this v naught y accompanied with j hat, then the addition of these two, nothing more than v naught, which is in here. And what's left in this equation is axt I hat plus ayt j hat. If you add ax I hat plus ay j hat in here, you get this. This is the equation, and this is nothing more than a, and that's all of it multiplied by t. A must be multiplied by t. Then you get this equation. So you can think of it in this way. Either this equation in two dimensions of motion, and you split it up into two equations, one along the x-axis and one along the y-axis, or you have two equations, you accompany them with this vector notation, v equal vx I hat plus vy j hat. Similarly for this one. And also you can see here r is in general represented at xi I hat plus yj hat, and r naught is represented as x naught I hat plus y naught I hat. If you put these two in the left hand side actually, and you subtract them, you're going to get delta x I hat plus delta y j hat. Now we decided to have two equations. Each equation has a constant acceleration in its dimension, one for the x-axis, one along the y-axis. So we have two motions. The motion along the x-axis, we have its equation, v final equal v initial plus ax multiplied by time, and the corresponding one on the y-axis give you the y component of the velocity. Again, if you have delta x along the x-axis, which has this equation in the uniform motion, you have a corresponding component along the y-axis, and then the final velocity along the x-axis is represented by this, and the corresponding one, the square of the component of the velocity along the y-axis is represented by this equation as well. Now we are going to set strategy for you to solve the two-dimensional problems. First of all, you have to define the coordinate system you are working on. For example, if you work in the Cartesian coordinates, and then make a sketch of the problem by showing the origin and the axes properly. And then you should know what are the given quantities in the problem, and what are the values and what dimensions. And then look at the question. What does the question ask for? If the question asks to find the x component of the velocity vector at the initial condition, it means v initial, or the components along the y-axis, the initial one, or ask you about the components of the acceleration in the problem. And then list the equations you want to use, and you have to decide which one is the proper one to use in your problem based on the known and unknown quantities. And then you have to remember that the time in the problem is the same for the x motion and the y motion, and also for the whole motion. Here, a little note we have to make before we go a further step. We're going to place from now and on the initial subscript for the initial position, for instance. We're going to replace it by naught, and also that for the initial component of the x component, the initial, instead of I, we're going to call it v naught x, and instead of saying vy v sub yi, we're going to say v sub naught y. That's to indicate the initial quantities in this problem, in the coming equations. Now, once you have an axis along each direction of the motion, you should know which quantity is along the direction of the acceleration, or which quantity is opposite to it. Obviously, the one you have to consider the signs in here, and for y axis and for the x-axis as well. And writing up all these equations and start solve the problems in order to find the unknowns. This is an application to two-dimensional motion with constant acceleration. This is about a fish swimming in xy plane. The initial velocity of the fish is 4 I hat plus j hat meter per second at a certain point in the ocean. With respect to an initial position, also with 10 I hat minus 4 j hat. After the fish is swimming with a constant acceleration for 20 seconds, its velocity becomes 20 I hat minus 5 j hat meter per second. Now, what are the components of the acceleration of the fish? in A and B, what is the direction of this acceleration with respect to unit vector I hat. That means with respect to the positive x-axis. Now if the fish, this is the third part of the problem, if the fish maintains constant acceleration, you are asked to find its location at time 20 seconds later of its motion, and what is the direction of this position vector. Here the fish is located with the initial position r sub I. This is the initial position, and this is the velocity vector with 4 I hat plus 1 j hat meter per second. And the expected answer for A is 0.8 I hat minus 0.3 j hat meter per second square, where for the position or the direction of the acceleration with respect to a vector is 339 degrees, and the position of the particle at a later time of 20 seconds is going to be 360 I hat minus 72.7 j hat meter, with an angle of 11.4 degrees below the x-axis. Well, to solve this example, let's put after drawing the sketch of the fish, let's put the information we have in the problem. The initial position is given as 10 I hat minus 4 j hat meters. The initial velocity is given as 4 I hat plus 1 j hat meter per second, and the final velocity after a time of 20 seconds is given as 20 I hat minus 5 j hat meter per second. Now, knowing all these, as you know, we have the first question is to find the direction of the acceleration vector, or we can find as well the acceleration vector if we are able to find the components of this acceleration vector. So to do that, we have to separate this equation into two equations, one along the x-axis and the other along the y-axis. To find the component along the x-axis, which is nothing more than Vx final minus Vx initial, that's divided by t. This is the first equation. What is Vx final? Vx final is this, and what is V initial? V initial is that. So by inserting 20 minus 40 meter per second and divide that by the period of time of 20, we're going to get 0.8 meter per second square for the component of acceleration along the x-axis. Similarly, doing that for the y-axis, knowing the x component of the final velocity as minus 5, and knowing the initial velocity component along the y-axis with 1, so we have minus 5 minus 1, divide that by the time, which is the same as we said before for the x-axis and the y-axis, we're going to get minus 0.3 meter per second square for the y component of the acceleration. Now, to get the direction, simply we have theta for the acceleration is tan inverse of ay divided by ax. Just insert the values and consider the sign as well. As you know, the one component is in negative and the other is positive, so the answer is we got 339 degrees for the angle of the acceleration. To find the position at a later time and its direction at a later time of 25 seconds. Now, what is constant here is just the accelerations we have and the initial motions. What is constant here? Ax and ay, and also we can take the initial values for the x component and y component of the velocities. Now the unknowns are written in there, so we set up this equation is the proper equation to find our unknown, which is delta x, and this is the one-dimensional motion, and that's nothing more than vx initial, and we have it here in the problem, and we have also x naught, as you know, along the x-axis, that is 10 meter. You put it on the other side of the equation. From here we got x initial to the other side, and then we put it in here, and also we substituted all these values into this equation to get 360 meters. That is the final position. That is the final position. And now again we're going to do the same thing for the y motion. Delta y equals to this known equation in one dimension, and substituting all the values available in the problem, and then we're going to get an answer for the final position along the y-axis of minus 72.7, and these are the values obtained from the above equation. Also for theta sub r, for the final position, we're going to divide the x component of final position by x and take the tan inverse, and then you're going to get tan inverse of this as minus 11.4 degrees, and this is the answer. The well-known applications for the two-dimensional motions can be mentioned in here. One of them is the projectile motion, and then the circular motion and the relative motion. In this course, in this chapter, we're going to handle the projectile motion together with the circular motion, and the relative motion will be probably left to another course.